Goal: to establish the American industrial base as the fundamental, non-replicable advantage that made rapid military adaptation possible. It wasn't just what they built, but how much and how fast they could pivot production. 1. The starting line: unprepared but untouched. In the autumn of 1939, as the Wehrmacht steamrolled Poland, the U.S. Army ranked 19th in the world, smaller than Portugal's. Its tanks were obsolete, its doctrine hesitant, and its military production negligible. Europe and Asia were already defined by total war, with factories in Britain, Germany, and the Soviet Union under the constant threat of bombardment. Yet, the geographical immunity of the United States was its first and most decisive strategic asset. Separated by two vast oceans, the American industrial heartland, Detroit, Pittsburgh, and the Great Lakes manufacturing centers could operate 24 hours a day, 7 days a week, without fearing a single enemy bomb. This stability allowed for unparalleled, uninterrupted planning and scaling. 2. The sleeping giant wakes, shifting production paradigms. When President Roosevelt declared the U.S. the arsenal of democracy, this was not just rhetoric. It was a blueprint for mobilization on a scale the world had never conceived. The key was the willingness and ability of established American corporations to radically convert their operations. Automobile manufacturers, accustomed to rapid annual model changes and high-volume output, were uniquely suited for this flexibility. Ford's Willow Run. This was the paradigm-shifting symbol. Henry Ford's vast plant, initially designed for cars, was retooled to produce the B-24 Liberator bomber. At its peak, this single factory produced a 4-engine bomber every 63 minutes. This applied the automotive assembly line technique to complex military hardware, turning aircraft production from a bespoke craft into a high-speed, standardized manufacturing process. Chrysler Tank Arsenal. Built specifically for war, this facility adopted conveyor belt assembly for the M3 and M4 series of tanks. This efficiency allowed the U.S. to manufacture M4 Shermans at a rate faster than all German tank production combined for most of the war. This ability to convert and ramp up production provided the capacity for adaptation. When the need arose for a new, larger gun or heavier armor, it didn't require a redesign of the national strategy. It required retooling a section of the existing production lines. The sheer scale, drowning the access in material. The figures detailing American production are almost mythical and represent the true power behind the Allied war effort. Adaptation wasn't just about designing a better weapon. It was about the capability to deploy an overwhelming number of slightly inferior or continuously improved weapons, negating the Axis's initial quality advantage. Product category: U.S. World War II production total, approximate. Significance for adaptation: aircraft, 300,000. Allowed for mass replacement of combat losses and the rapid deployment of new models, e.g. transition from P-39 to P-51. Tank/self-propelled guns, 88,000. Enabled continuous field upgrades and the ability to absorb heavy losses while maintaining offensive momentum. Merchant ships, Liberty and Victory, 5,700. Provided the logistical backbone, Act V, necessary to transport every weapon and adaptation to global theaters. Machine guns, 2,700,000. Ensured every soldier had standardized, reliable, and easily replaced small arms. This colossal output meant that U.S. forces could field test a weapon, find its flaws, and have a redesigned or entirely new version arriving at the front before the initial batch was even fully consumed. The M4 Sherman, though often criticized, was the perfect symbol of this. It was a standardized, reliable, and easily repairable platform that was constantly rapidly improved, Act 7, because the production lines were always running. To detail the groundbreaking organizational structure that ensured scientific and technological breakthroughs were rapidly integrated into military doctrine and production, circumventing bureaucratic delay. 1. The need for speed, recognizing the technological gap.
By 1940, the U.S. military realized that traditional, slow-moving War Department bureaucracy was incapable of matching the pace of technological development set by Germany, especially in rocketry and jets, and Britain in radar. The military-industrial complex, as we know it today, did not yet exist. Scientists often struggled to get their ideas heard by skeptical military procurement officers. A new model was desperately needed to harness America's powerful academic and industrial research talent. 2. The birth of the OSRD, the Civilian Superagency. In June 1941, President Franklin D. Roosevelt, recognizing the urgency, bypassed the traditional military structure to create the Office of Scientific and Research and Development, OSRD. He placed it under the leadership of Vannevar Bush, a civilian engineer and former dean of engineering at MIT. Vannevar Bush's mandate: the OSRD was given immense power and a staggering budget, reporting directly to the president. Its sole mission was to mobilize American scientific personnel for war and, crucially, ensure that technical solutions were moved from the laboratory, the pilot plant, and the factory to the battlefront. A unique structure. Unlike military research agencies in other countries, the OSRD was composed primarily of civilian scientists, engineers, and academics. This structure fostered faster decisions, eliminated military rigidity, and allowed for intellectual freedom and collaboration that few other nations could afford. The radar revolution, the MIT Rad Lab. The OSRD's crown jewel, and the clearest example of rapid adaptation, was the Radiation Laboratory, Rad Lab, established at MIT. While Britain had pioneered early radar, the U.S. excelled in refining and mass-producing it. The cavity magnetron. After receiving the highly classified British cavity magnetron, a device capable of generating high-power microwaves, shrinking radar size, the Rad Lab rapidly engineered it for mass production. Size and versatility. U.S. adaptation reduced the size of radar units from large ground stations to devices small enough to fit into the noses of night fighters and even the bellies of anti-submarine planes. This gave the U.S. and Allied forces unparalleled advantages in everything from night combat to U-boat hunting and accurate naval gunnery. This immediate scientific application directly translated into tactical superiority. Beyond the battlefield. The medical and material impact. The OSRD's scope extended far beyond conventional weaponry, demonstrating a holistic approach to warfighting and troop readiness that amplified the effectiveness of the entire force. Penicillin. The OSRD pioneered the techniques for mass production of penicillin. Previously a rare laboratory curiosity, American industry, under the OSRD guidance, ramped up production from almost nothing in 1942 to enough to treat every Allied wound by 1945. This dramatically reduced battlefield mortality and recovery time, increasing the rate at which experienced soldiers could return to combat. Proximity fuses. Another critical OSRD-developed technology was the variable time proximity fuse. This tiny radar device, built into the tip of an artillery shell, detonated near the target rather than on impact. It turned traditional artillery into highly lethal anti-aircraft weaponry and made ground barrages far more effective. The U.S. held this technology back until the Battle of the Bulge to prevent the Germans from capturing and replicating it, showing strategic control over its scientific advantage.
To explain how American military doctrine, unlike the more rigid and centralized doctrines of the Axis or even the Soviet forces, was built to encourage speed, flexibility, and adaptation at the lowest possible levels, enabling faster tactical learning. 1. Doctrine versus dogma, the philosophy of command. Most armies enter a war relying on the doctrines they honed during peacetime. For Germany, this meant rigid Auftragstaktik, mission-type orders, but often coupled with a centralized cult-of-personality command structure. For the Soviets, it was often high-level strategic direction with limited on-the-spot authority. The U.S. Army, heavily influenced by its experiences in decentralized multi-front campaigns, like the Pacific Islands in North Africa, deliberately fostered a doctrine of initiative and independent judgment. The Marshall Principle. Chief of Staff George C. Marshall emphasized that commanders should be trained to think for themselves and operate effectively even when communication broke down. This was especially vital for the vast distances of the Pacific Theater and the fast-moving armored drives in Europe. Encouraging feedback. Unlike armies where questioning orders could lead to severe consequences, the U.S. system was designed to allow reports and critical feedback on everything, from equipment flaws to tactical failures, to flow up the chain rapidly without fear of reprisal. This created a culture where learning was valued over obedience. 2. The power of the unit commander. The American system invested significant trust and authority in unit commanders at the colonel, major, and captain levels. This meant that adaptation to local conditions, the key to winning complex battles, could happen almost instantly without waiting for permission from headquarters many miles away. Adaptation on the fly. The hedgerows. A classic example is the fight in Normandy's bocage, hedgerow country. Initial American armored tactics failed miserably as tanks were easily ambushed by concealed German anti-tank guns. A non-commissioned officer, Sergeant Curtis G. Coolin, adapted scrap metal and German obstacles into a Rhino tank hedge cutter prototype. Instead of waiting years for an ordnance board approval, Coolin's idea was immediately adopted, fabricated by local depot workshops, and rapidly field-modified onto thousands of Shermans, effectively solving a major tactical problem in a matter of weeks. Decentralized air support. The U.S. Army and Air Force pioneered highly effective close air support coordination, empowering forward air controllers, often captains or lieutenants, on the ground, to call in rapid airstrikes from nearby fighter-bomber squadrons. This ability to integrate fire support instantly was a massive tactical advantage over armies that required hours of bureaucratic routing for air requests. 3. The logistical guarantee. This decentralized doctrine, Act 5, was only functional because of the massive industrial backup, Act 1, and the efficient logistical system, Act 6. Commanders could take risks and adapt their tactics, knowing that replacements and resupply were guaranteed. If a commander needed to convert a supply truck into an impromptu armored vehicle, as sometimes happened in North Africa, they knew they could draw replacements later. If a unit suffered heavy losses due to a flawed tactic, the replacement troops and equipment were already moving up the supply line. This logistical safety net removed the paralyzing fear of irreplaceable losses that haunted German and Japanese commanders, encouraging aggressive, adaptable behavior. 4. Training for flexibility. American training centers, particularly those handling rapid expansion and officer commissioning, focused on flexibility and problem-solving rather than rote memorization. Training scenarios were designed to break down communication and force junior officers to make high-stakes, autonomous decisions. Overseas replacement depots. Even replacement troops flowing into combat zones were quickly integrated into existing units and given rapid, current battlefield training based on the latest reports from the front, not on year-old manual doctrines.
to demonstrate how the American industrial commitment to standardization, driven by peacetime consumer manufacturing models, translated directly into military superiority by making every aspect of warfighting, from training to repair, easier and exponentially faster to adapt. 1. The core philosophy: interchangeability and simplicity. While the Axis powers, particularly Germany, often prioritized highly specialized and technically sophisticated equipment, like the Tiger tank, the U.S. focused on the concept of interchangeability. This principle, the bedrock of American manufacturing since the late 19th century, meant that any part for a given model could fit any other unit of that same model, regardless of which factory produced it. Logistical genius. This was a logistical superpower. When a tank broke down in Normandy or a plane was damaged in the Pacific, field maintenance crews didn't need a specific artisanal component flown in. They needed a part from the nearest depot, guaranteed to fit. This drastically reduced the time needed for repairs, keeping equipment adapted and fighting. Training efficiency. Standardized equipment meant that a mechanic trained on an M4 Sherman in Texas could immediately repair any Sherman anywhere in the world. Similarly, a new pilot could transition quickly between aircraft models produced by different companies, like North American versus Curtiss, if the controls and basic systems adhered to the same standards. 2. The case study: the M4 Sherman platform. The M4 Sherman tank perfectly embodies this principle of standardized adaptation. It wasn't the most fearsome tank, but it was the most adaptable and available platform of the war. The common chassis. The Sherman was built around a common, robust chassis. When the Germans introduced better anti-tank guns, the U.S. didn't waste time designing an entirely new tank from scratch. They leveraged the standardized chassis to rapidly mount better guns, like the high-velocity 76mm gun, and thicker armor, up-armored jumbo variants, or repurpose the chassis entirely for specialized roles. Flexibility and firepower. Crucially, the Sherman's chassis was standardized enough to be quickly converted into numerous specialized variants: tank destroyers, M10/M36, armored recovery vehicles, self-propelled artillery, and even rocket launchers. This ensured that adaptation to a new tactical threat could be met with a new vehicle, all flowing from the same high-volume production lines. 3. The Liberty ship. Standardized victory on the seas. The standardization philosophy extended far beyond the battlefield vehicles and was most famously applied to the merchant marine. The Liberty ship was not a technologically advanced vessel, but its simplicity was its strength. Massive output. Using prefabricated sections manufactured by dozens of different contractors across the country and welded together quickly, the U.S. drastically cut construction time. What once took a year now took as little as 42 days, and famously, one ship was built in under 5 days as a stunt. The logistical lifeline. These standardized, easily repaired ships formed the backbone of the logistical colossus, Act 6. They ensured that every technological adaptation developed by the OSRD, Act 2, and every replacement part needed by the commanders, Act 3, could be reliably and quickly delivered to global theaters. 4. Continuous improvement versus perfect design. Standardization allowed the U.S. to implement a doctrine of continuous improvement. German military production often favored meticulously over-engineered designs, like the Panther and Tiger, which were difficult to manufacture, required vast resources, and were nearly impossible to repair in the field due to their complexity and lack of parts interchangeability. The U.S. philosophy was to rapidly produce a good enough weapon and then integrate improvements on the line, ensuring that the newest, most adapted version was always rolling off the factory floor.
The seamless path from foxhole complaint to factory floor fix. Go. to illustrate how the U.S. military uniquely institutionalized the process of learning from combat errors, ensuring that technical and operational flaws were diagnosed, resolved by scientists, and corrected in mass production faster than any other major combatant. 1. The institutionalization of learning. Every major army experiences equipment failure and doctrinal setbacks, but the U.S. military was unparalleled in its ability to institutionalize critique and treat every combat action as a data-gathering exercise. This was not simply a suggestion. It was a formal process driven by dedicated organizations. Army Ground Forces, or AGF, and Army Air Forces, or AAF, boards. These dedicated organizations had representatives whose job was to travel to the front, interview troops, collect damaged equipment, and write detailed reports on what worked and, more importantly, what failed. This direct, unfiltered feedback bypasses multiple layers of command that might otherwise dilute or bury bad news. The war colleges and staff, unlike previous conflicts where lessons were learned and applied after the war, the U.S. system funneled these AGF and AAF findings directly into curriculum revisions, officer briefings, and, critically, technical specifications for new contracts. The learning was real-time. 2. Case study. The torpedo scandal. Naval adaptation. Perhaps the most dramatic example of a major flaw being corrected through systemic adaptation occurred in the U.S. Navy. Early in the war, American submarines were launching thousands of torpedoes that either failed to detonate or ran too deep. This wasn't a manufacturing issue. It was a design flaw in the magnetic and contact detonators, compounded by peacetime testing failures. The failure of tradition. The Navy's Traditional Ordnance Bureau initially resisted the complaints, blaming the submarine crews. The triumph of evidence. Submarine commanders, operating under the Decentralized Doctrine, or Act 3, began independently running tests and gathering irrefutable photographic evidence of the failures. This evidence, bolstered by congressional pressure and the OSRD's technical expertise, or Act 2, finally forced the Ordnance Bureau to concede. The swift fix. Once the flaw was confirmed in 1943, the full force of American science and industry, or Acts 1 and 4, was brought to bear, resulting in redesigned detonators and warheads being mass-produced and installed globally within months. This one fix dramatically turned the tide of the Pacific Submarine War. 3. Case study. The Sherman's flammability. Ground adaptation. The M4 Sherman tank, while standardized, or Act 4, and numerous, or Act 1, had a critical flaw in its early design. The placement of its high-octane gasoline engine made it vulnerable to fire when hit, leading to the grim nickname Ronson. The feedback. Frontline reports confirmed the extreme vulnerability and demanded a solution. The adaptation. The solution was twofold and rapidly applied. 1. Production was immediately shifted to the M4A3 and later models using a less flammable Ford-designed diesel engine or a safer engine configuration. And 2. Every existing Sherman was retrofitted with wet stowage, storing the ammunition below the waterline or in protective tanks, which significantly reduced the risk of catastrophic fires. This was a massive, multifaceted adaptation involving millions of dollars and thousands of workers, implemented globally during the campaign, demonstrating the ability to simultaneously upgrade existing stock and shift new production. 4. Continuous flow of technical orders. This adaptive cycle was codified into the Technical Order System for the Air Force and the equivalent systems for the Army and Navy. Whenever a flaw was found, a TO was immediately issued, detailing the problem and the required fix. This order was instantly prioritized by the logistical chain and often executed by mobile field units before the aircraft or vehicle was even pulled from combat duty. This constant flow of corrections and upgrades kept the American arsenal on the cutting edge.
To conclude the argument by highlighting the American ability to rapidly and consistently train, replace, and integrate millions of adaptable soldiers and sailors, ensuring that new doctrines and equipment, Acts 3 and 7,
were effective across the entire global force. The power of the personnel pool. The fundamental difference between the American effort and that of its adversaries lay in the depth and quality of its human resources. Unlike Germany and Japan, which mobilized nearly their entire industrial and agricultural workforce into the military, the U.S. could maintain a massive, highly productive civilian economy, Act I, while simultaneously drafting and training millions of men. This provided a constant, high-quality stream of manpower. Educated workforce. American draftees arrived with a higher average level of education and technical literacy than those of most other nations. This made the rapid absorption of complex OSRD-developed technologies, Act II, like radar, complicated gunnery systems, and advanced maintenance procedures, far more efficient. The GI Bill incentive. Even during the war, the promise of the GI Bill served as a subtle incentive, encouraging adaptability and competence by tying military service to long-term educational and economic benefits, fostering a more motivated force. Standardization in training, the great American machine. Just as equipment was standardized, the massive training apparatus was standardized to ensure every soldier, sailor, and airman received consistent, high-quality instruction regardless of their initial induction point. Rapid commissioning. Officer Candidate Schools, OCS, rapidly produced thousands of junior officers, deliberately focused on the decentralized command principles of initiative and problem-solving, rather than rigid, outdated protocols. Specialized schools. The U.S. established dedicated advanced schools, e.g. amphibious warfare schools, specialized aircraft maintenance schools that constantly updated their curriculum based on the latest combat reports, Act 7. These schools acted as secondary nodes for distributing technical and doctrinal adaptation. The Overseas Replacement Depot, or ORD system. The most critical mechanism for sustained adaptation was the efficient Overseas Replacement Depot, or ORD system. This system ensured that the constant flow of replacement troops was not just numerically sufficient, but tactically relevant. Fresh knowledge, not just fresh bodies. Instead of shipping replacements straight from basic training in the U.S. to a combat company, ORDs were established near the front lines. Here, troops received several days or weeks of intense finishing training based on the most immediate, up-to-the-minute lessons learned from the nearby battlefield. Rapid integration of lessons. If the Germans began using a new anti-tank tactic in the Ardennes, that lesson was taught to new replacements at the ORD within days. This immediate, localized curriculum update guaranteed that every replacement soldier was already adapted to the current threats before they even met their new unit. Sustaining the adaptation. By maintaining a huge, educated, and continuously trained personnel pool, the U.S. could afford to rotate commanders and personnel out of combat to prevent burnout and back into training centers and staff positions. This allowed combat veterans to directly teach the next generation, embedding adaptation into the very fabric of the fighting force. This cycle of rotation and retraining was essential for long-term strategic adaptability.